So here's my attempt at translating that description of an algorithm into actual Python code. I ended up using a couple structures maybe a little bit differently than before. So I've got a Dijkstra algorithm. Dijkstra is the name of the individual who first described and analyzed this algorithm for a single source shortest path, right? So we give it a single source, we give it a single node in the network, and we ask for the distance to all the other nodes in the network in graph G. So the distance so far is a structure that's going to represent a mapping from nodes to what we think the distance might be from V to that node. And in our hand-simulated algorithm, these are the numbers in the non-locked circles. Some nodes might not have any numbers yet, and the ones that have numbers are represented in that mapping. So then we start that structure off by saying, well, the distance that we know of so far from V to the V, the node that we started at, is 0. And we did that in the hand simulation as well. All right, now there's an additional data structure, which I call final dist, which is once we actually figure out what the real distance is, we stick it in this structure. And so that's basically the numbers that are in the heavy circles here. When a circle becomes heavy because I'm locking it down, I move that number into the final dist mapping, and I delete it from the dist so far. So that number doesn't exist anymore in the dist so far mapping. So now we're going to iterate as long as the set of nodes for which we've computed a distance is less than the total number of nodes. Now this is a little risky. I probably shouldn't have done this because if the graph is disconnected, what this is going to do is it's going to die. Well, we'll see where it's going to die, but it will keep trying to add nodes, their final distances, even though there aren't final distances to add. So there's probably other tests that might be better to determine when everything that's reachable has actually been assigned a value. So in general, this test isn't quite the right test, but it will suffice for a connected graph, and that's what we're going to try it on. What do we do? As long as there's more nodes that we need to analyze, take the node that has the shortest distance of all the ones so far, call that W, and lock it down. So locking it down in this case involves me printing a debugging message saying that the final distance for W is whatever we computed the distance so far as. So we've gotten we now know that this is the final distance, and then we delete that from the dist so far structure. Then we go through its neighbors. So all of the neighbors of neighbors of W in the graph, call them X, and for each one we'll say, well, if we haven't already completely solved that node, if we've completely solved that neighbor, then we don't have to do anything. But if we haven't, then see if it has a distance so far. And if it doesn't, then give it one by saying, well, our best guess as to the distance is going to be the distance that it took to get to W plus the distance from W to X. On the other hand, if it already has a distance, check if the new distance, the distance to W plus the distance from W to X, is better than the distance that we had so far. And if it is, replace it. This is sometimes called relaxation. It doesn't seem very relaxing, but that's what it is. And so now we've handled that node. We handle all the nodes for the neighbors of W, and that means we've handled W, we've locked it down, and we can move on. So we go back up and handle the next node closest to the start state. And once we've gone through all of the nodes and assigned them all their final distances, then we return that structure and we're done. So this is the Dijkstra algorithm in a nutshell. Let's analyze this.